Good afternoon. So there will be no lecture this Friday, and because and also no office hour for tomorrow, but we will have lecture for the coming month. So let's continue with the inheritance. So the main idea of this inheritance is try to reuse functionalities. Okay. For example, I think that this is where we stop from the last class. If we have already defined a class called person, we define constructor, some attributes, some actions can use, but then we want to define each person. Basically, just want to enhance the person a little bit with additional age information. So if we do not use any inheritance, we just try to recreate another class from scratch. As you can see, we basically rewrite the majority of the code. But there's we can be a little bit smarter by reuse the person's class. For example, the person class, as you can see, we have a constructor. The constructor initialize instance attribute called name. Okay, then you can define a get name to return the person's name. Okay, so for example, if you define a person Bob, then you can say print p.getName. Okay, that is what we have seen before. So now if I create an age person, and now this is something new. As you can see, now we have a parenthesis and passing a class name. That means this age person will inherit from person. Okay, so by inheriting, that means it will everything defined in parent, it at your control. You can directly reuse them, or you want to modify it from them. Okay, so the age person choose to just directly take the get name, but the age person want to do a little bit its individual or its specific constructor by say now init will take name and take age. It will try to do cf.name and cf.age. So it basically create one additional attribute. So and also it try to adding another get age. But remember, we never define the get name for age person, but by inheritance, that is by default, the age person can use the get name. Okay. So there's something else we can do is just remember to refer to our object self, you can use self, right? So we also, for the parent, we're also using something we call super. So basically you can reuse functionality even more by using the super function within a child class. So tell the class to inherit this method property from the parent and allow further refine. For example, for the init, remember the constructor for the age, it's taking name and age, but you can even make things more smart. It's called super do init name. That means I create a constructor, okay, and this constructor is first try to call the constructor of the parent. Try basically, of course, in this example, it's very simple. You just, when you call this, is just to try to save you one line of the code to pass the name to your instant variable called name. But imagine you have a very complicated constructor for the parent. Yes.
Could you, if the parent class was also a child of another class?
Yeah, of course. Yes, in the I would say for those cases, I encourage try out for the other. There's many questions we can ask, but to answer this fundamental question is everything in Python, they are inherited from some parent object class. So we will talk about that. So basically everything you inherit. But for those many situations, like last time I talk about when you can use, you need to use self, when you're using class name. There's many designs in Python. So I will say, if you really want to master the Python, this class is just give you some introduction, really some basic introduction, so you can start to write code for data side. But if you really want to master Python, go back and try your questions and see when it works, when it fails. Because most of the things is really by design. It just depends on how the Python are defining things. Because even in Python 2 and Python 3, things can be defined inside differently. So what I told you, maybe it's true for Python 2, which not necessarily for 3 or something. So those things, but the key here is try to understand what is an object. Try to understand the concept of you can inherit from parents, those things. Yeah. So here is basically you can, if you have a very complicated constructor for your parent, by using super.init, actually you save a lot of code, right? Because basically you essentially you do what the parent's supposed to do. Then you adding additional, say self.age equal to age. So you're adding your specific code there. So I hope this is give you a good idea how this can be used. And also of course, here is you still need to define your own get age. So this is what actually I just want to mention. All classes in Python inherit from the building basic class called object by default. So there's a grammar type of class there called object. And in the object, they define a few things which we already use, but probably we are not aware they are existing there. So for example, string, I think that we see this. Remember, we have one example called multi-list or some multiple list or something like that. Do you remember? We redefine the string and we try to print a list of list. We try to redefine the string and make the printing a string in a special effect as we want. Okay, so that is what the string control. And also there's another called rep, probably means a representation. That is an official string representation of an object. If you do not rewrite, or we call override. If we do not override those default methods, it will try to using what defined in the object class in this grandparent object class. But you can choose to override. Okay, once you override it, then your method start to become this child specific one. Okay. So basically the representation, the rep is the official string. And then this underscore string is an informal string. Let me bring this. Okay. So for example, we can define, let's say for the age person, we can define representation, our own representation function we call self.name, comma, self.age. So now if we do rep, you can say it will print Bob, comma, 33, as you can see. If you do not do this, of course, you can go back in the Jupyter Notebook typing. If you do not define this, and then you call rep p, see what it produces. Okay, I'm sure it will be less readable or less meaningful, but now you are customized into a way you want to output it. Okay, I hope this. Any questions so far? The uses of inheritance, we have C. For example, each time when we import from sklearn or from a couple of libraries we have used, I believe we have say like a linear model, and actually the linear model was inherent by linear regression, ridge regression, because when you talk about linear regression, talk about ridge regression, I guess you will appreciate more about this inheritance, right? Because those things, they are really more or less very similar. They just, each of them is a slightly revised version of the other. So you can start with something in common. Then you try to adding each additional component, right? So, I mean, when you really write more serious code for data science, you will find this parent-child inherent object concept will be very convenient because you do not need to rewrite everything from scratch. You just do a small modification to what already be there. And also there's a, if you take a object-oriented programming language, I believe you will be spend more time to appreciate other properties like polymorphism, like interface, those concepts. So for the polymorphism is basically the general idea or general intuition here is if other object they define some of the actions and you just try just like what we call like something let's say we always call something fit a data, right? So you here we give example. For example, if you just know as long as an animal they will always have a talk function, okay? But what sound does try to talk is a dog talk, is a cat talk, is a cow talk. It really depends on what object is try to what you have at the moment. Okay, so this is a bring a lot of convenience. For example, in a particular example, we try to say, oh, hey, there's an animal class, and we will try to do something like this. We will try to define a talk, but we for the parent class, we don't really define anything, but we just try to say, if you don't implement this talk, I will try to raise a error. So that means as if you inherit from me, you have to have a implementation called talk. Okay. So now I will have a cat. A cat I inherit from animal, and then I define a talk. Then I return meal. So this is the example I try to say. You inherit from your parent, and you have to implement something. Okay. So for example, if you have another, let's say class dog also inherit from animal, then you also define talk, which return, I don't know what dog spelling, but the dog will make the dog sound. So in this way, when you create a particular animal actual object, a cat object or a dog object, you will be always say cat some object called talk or dog talk. They will play individual or their specific, the object specific sound. And also, of course, you can also achieve this without doing inheritance, but then you need to define things and you need to define a talk, then you return quack. But after you do this, you can do something cool as follows. You can say there's a list called cat something, and dog. You create three animals. Now you can just print in animal.name, animal.talk. Then this will give each individual, like you are using a unified way to operate on them, but you will get a different sound. So I hope you appreciate this example. Any questions about this particular example? So in this way, you will know all the animal object. They will have certain actions. You just using a very neat way to invoke them. Okay. So let's go to the Jupyter notebook. So any questions about the example? Oh, we are okay, right? So this so in this example, we start with a parent class called vehicle. So the vehicle has a constructor. The constructor will initialize the price, and then also it has a function or action called display price. Then it has a string. You try to to return when you print the vehicle, it will show its displayed price. So then we create another named vehicle from vehicle. So basically, this is still inherit all the price information and the price function. If you do not want to do anything, essentially you already have everything to handle the price. But now you want to adding additional name to your class. Okay, so now basically you you can call your parent and yeah, so this is something which is as we highlight here. If you do not, because we from the lecture slide we have see we can always do this using a super, right? So if you do not want to using super, you can using the vehicle init, but this time you have to pass your self as an attribute here. And basically this is still the functionality is still the same. You invoke your parent constructor, and after that you just try to adding your own attribute, which called name, right? So you redefine an additional method called display name, and then you define a new string method which override your parent method. So your parent already defined a string method. So now you define your own string. So now if you belong to a named vehicle object, you are using your overwritten method to call the string for the print. So now let's say I create an object called name vehicle. I passing the price, then passing the brand. Now you say you can do display name, display price. You can say you have name, you have a vehicle, and if you pay attention to say the object dot display price. If you just look at the child function, you don't see the display price, this message, right? So this is a cool part because the display price is belong to the parent. So you can still use with no problem here. Okay, so just try to understand why it can use the display price. So this is a because it's borrowed from its parent class. All right. Any questions about this first example? Two things, as I mentioned. One is the child object can use its parent function with no problem. The second is if you do not want to use super, you can use this way to invoke the parent function. Then again, go back to play around, and if you have questions about whether this work or that work, you can try to play a little bit and see how things are to get a better understanding about this. And this is another very cool example. So we have a quadrilateral parent object, and then of course here we have a four side, which is common. Then we have but then we have several different forms. We have a rectangle, we have a square. Okay, so the rectangle inherit from the parent class, and then the square inherit from rectangle class. As you can see, this kind of inherit can be layer by layer, because this is not surprising, right? As I just mentioned, everything you are inherent from some grandma class called object. Yeah, so this is a kind of, you can keep inherit. So but the basic idea is still the same. So rectangle, you just try to adding one more thing called area. Okay. And when you have a square, you will try to, because for the square, now we all know square have a, yes, questions.
super result into just A, not A.
We can't because you need a 4 parameter to input, right? So, but for the rectangle is hidden inside, so the rectangle it only take AB, but it's only inside. You expand it to AB, AB.
Yeah, so the last two parameters are not
It matters when you are using this function because otherwise you can't use this function. This function expect you'll have four sides to be input, right? So if you're only using AB, you can't. This function doesn't work, right? Because the last two, the size 3, size 4, you have nothing to assign to. Yeah. So, and for the square, because square we know, although it has 4 sides, but they all have equal length. So we just need one value. So basically, you are just give one value, but since you are inherent from rectangle, so you just need to input 2 times, because this basically the AB, then AB will be expanded to AB to use the parent class to initialize. Okay. So then again, for the area, it has because when you have a squared, you have a little bit different way to compute the area, right? Because you just raise to power, so you have define your specific way. I hope you get a feel. This is a very simple example. The actual code doesn't do anything, but it should give you a very good understanding about why we need this type of inheritance. Okay. So then we can do a couple of things, because this is this example is try to tell you the area is only defined in a child class. The parents class cannot use that. The child can use parents function, but parent cannot use the child function. This is pretty much the same thing, and yeah. Then the other things is you need to because when you do the square, remember the square is you need to 4 sides need to be equal. Okay, so sometimes when you using the previous simplified version, you may have a problem to enforce the 4 sides to be equal. So sometimes when you are writing a safer code, you want to do some check. So like this is a assert. Assert is try to assert. When you do assert, is try to say the if this condition for after that is true, then nothing happened. If it's false, then it will try to throw a assert error. So a lot of time we do the assert try to indicate there's something which unplanned happened. Yeah. Okay. Yeah. So this is a pretty much what I try to say. And go back to go through those code. If needed, you can always type in and try it out. But any questions so far about the inheritance? Are we okay with this concept? Great. So let's move on. By the way, we have released homework 10. So you guys have seen that, right? So it's about some supervised classifier. We include 3 classifier there. One is a k-nearest neighbor, which we have seen from last class. And then we have another we call SVM. SVM is we will touch a little bit. Actually, we didn't put a name, but this figure is about the SVM. Okay, so I will give a little bit more detail about the SVM, but that is something we will not talk in details during the class, but we give some introductions, very simple introduction about the SVM. And then we have a tiny neural network type classifier. We will cover that probably in a week or two. So that homework is a new homework, as I try to say. Please bear with us if there's any errors or any places which try to raise that during the office hour if you made problems. That is try to give you some understanding how to do some simple classification with some very tiny images. And we found that it is interesting to at least that homework is actually pretty straightforward one. It's more ask you just experienced to have some experience, just run those classifiers to observe certain things. It's not super challenge in terms of programming. So you have plenty of time to do that and enjoy that homework. So today we will come to the another classifier called naive Bayes. It's because I talk about the care nearest neighbor first is because I want to make you be not surprised by homework 10. So I give you some very brief introduction. But this slide is actually designed come before the carriers neighbor. So let me give you another formal introduction to classification. So the classification is basically, I think I have covered this, is you get a data point and you just tell what class it fall into. Is it animal? Is this animal a mammal, a bird, or a fish? Is a picture a cat, a horse? So basically you assign these discrete labels to an object, okay, to a data points. So the key here is try to learn a classifier. A classifier, essentially you give a data point, then the classifier will try to assign a class label, okay? So that is a classification problem. So in general, you have a bunch of data points, x1, x2, x3, essentially, then each one is labeled with its class, and the classifier should be able to tell which class a new data points belong to, okay? And because we started with label data, so this is another example of supervised learning. Supervised learning means you know the ground truth for your training data. So for your training data, you know what each data point is actually associated with, and use that to guide your learning procedure. And unsupervised learning is something like clustering, right? Clustering, you have just a bunch of data points. You just know their value, and you don't know what they belong to, right? So that is called unsupervised. So for example, here, this give you an intuition to say, hey, there's three class of data points. And although we color them, but at the first place, you do not know how exactly to what is a rule or what is a decision boundary to separate them, right? Because you just get you know there's a different color, this pattern, but you need to find, hey, what is for example, what is the decision boundary you need to create to separate them. So if you really conclude your knowledge into this type of boundaries or decision or classifier or whatever we call it, and then a new data points arrive, then based on your previously learned classifier, you were able to infer what that belonged to. Okay, so we have one method we call carriers neighbor, right? That is just like if I have point falling here, then I just using its neighborhood to infer, hey, this is a orange star class. Okay, so that is a basic idea. So to define a classifier formally, so if we consider data points in a d-dimension space, okay, then each data point I is defined by d features written as a xi equal to xi1, i2 until until ID. That means the i's, because each is a value, right? Remember, we usually write each point as a vector. The vector has a d dimension because we have d different dimension of descriptions about these data points, right? So then each data I is from one of the k possible classes. Then we denote the i's class as yi belong to C0 until CK1. This is a more formal language. If you write a report, if you write a paper, if you write anything, if you want to write things in a formal way, this is a language. Okay. So this is a typical way we try to describe a problem. You say, hey, I have a k-dimension data. Then the I sample is written as this. Then I have a k classes and they belong to C0. So don't think this is unnecessary because this is the mathematical way to describe a data, describe a problem. So, okay. So almost many data science paper or writing in the math method part, you will start with this to state what problem you are. So then a classifier is a function that predicts a data point class. So then again, formally, you will write your classifier as a fxi. So basically, this classifier is a function. It will taking data points xi and output a yi hat. Basically, output a class label. So this is a mathematical formal way to write what is a classifier. And also the yi will belong to one of your class label. Okay, so I hope you are fine with it. This is a kind of very mathematical formal way to talk about classifier. So this is a kind of formal definition about classifier. So in this class, we will focus on two classes, which is k equal to 2. As I mentioned, sometimes we call this a binary classifier. And we will touch only slightly to the multi-class, but we will tell the basic idea using the two-class problem. So again, this figure, this cool figure here, is what we call SVM, the supported vector machine. This is actually your homework. Homework 10. The second question is ask you to use this classifier to separate things. Okay, because the sklearn has a SVM implemented, so we didn't actually give her how this actually learned because anyway, the way to optimize this classifier is beyond this class. So, but it's very powerful. This is one of the breakthrough, at least before the deep learning. I think that this is one of the most popular classifier. So I just want to give you some very, very basic idea here. So this is a SVM is actually a linear classifier. You try to you see you have blue points and the green points. Okay, so now I try to look for a decision boundary. I want to find where I want to draw a line to separate these two classes. Okay, so in later of the course, we will talk something called logistic regression. That is another linear classifier. So they are both look for decision boundary, but by following different loss function, they are trying to optimize slightly different things. So for logistic regression, I think that we will talk about it. Try to use some kind of logistic function to simulate some kind of probability. Then there's another loss to optimize. But here, the coolest part is the formulation of this classifier. It try to look for something which try to maximize the margin between those boundary data points. So if you have like a two bunch of data, right? So this classifier is try to optimize in such a way, it will try to find a line to be in the middle of a margin, because you can always try to find different way to draw a margin between the separation. So I'm looking for the maximum margin place. So use that as my decision region. Then you draw a line in between. Then, of course, based on some very simple geometry, you can write your margin in terms of 2 divided by norm of the weights. I mean, this you do not need to know this, but essentially you are optimized this term. So you will find. I just hope to use this simple example to show you some how cool the machine learning is. Yeah. So you are optimized this guy, and then you will find a weight, because the W here, we learn the W here, right? The W, when we learn linear regression, we know the W is actually indicate a line, right? So you are looking for a line such that this guy will be minimized. Then you, after you solve that problem, you will get a line. So this is called support vector machine. The reason is called support vector is because they are looking for a lot of those support vectors, those points on the boundary. Those is like they are supporting this decision. Yeah. So anyway, I just talk about this, and so you won't feel surprised you have a support vector machine problem for your homework. But believe me, it won't ask you much. It just asks you to call the sklearn, the SVM, and to solve some problem. Yeah, so it's straightforward. Any questions so far? Are we fine with this? All right. But if you take any advanced machine learning, this support vector machine is one of the things you will, for sure, you will learn that and you will enjoy. It's really smart. In this class, instead, we will talk the following a few things. We'll talk about naive Bayes, which is a very simple classifier, and this is what we are going to cover next. Very simple, but very powerful and also very smart. Yeah, Carey's neighbor, because this is such a short topic, so I just try to bring forward to prepare for your reception of this homework 10. We have already covered this. And then another big thing is logic regression. Logic regression is one of the major tasks we are going to go through together for the data science part. Because once you understand logic regression or carefully or completely know what is the intuition, what's in behind, it will help you a lot to understand the neural network. Because to me, I think the neural network is just another way to stack a lot of logic regression. Maybe some people disagree with me, but when we talk about that, you will see what I mean. Yeah. So if you put logic regression in a layer-wise form, of course, you need to bring some nonlinear activation layers, but essentially, it will help you to understand. Because the simplest neural network is we call perceptron. Perceptron has a very similar form to logic regression. It's almost equivalent, except they have one component different. We will talk about that later. So today we will talk about this naive Bayes. Just like name, it makes some naive assumption. So basically, it try to simplify things. It try to assume independence. Okay. So the basic idea here is try to, because a lot of time you'll have a complicated model because you assume certain things they are correlated, they have relationship. But if you are able to be brave enough to assume a lot of independence, your model will reduce to a very simple model, and you make some decision very quick. Okay. So the basic idea is each class of data can be described by a probability distribution, show how likely different data points are. If you have a new data points, then which distribution is it more likely come from? When I read this, do I remind you anything? Looks like it remind me something, right? It remind you the GMM model. Does it? Right? So GMM model, essentially, you are thinking you have, although there we are doing clustering, but you also assuming there's several different distribution module there. Then especially for the in step, you will try to compute some kind of likelihood, right? To compute the likelihood, you will try to say, hey, there's a few things. Well, how likely this distribution will appear? When distribution appear, how likely it will make this observation? That essentially what we're talking about this, the second line, right? If you have a data points, what distribution is more likely to come from? This is essentially the likelihood term we are trying to compute, right? I hope you see the link there. Yeah. So for example, we have a super simple example here. We have two classes of cars. We have sports car C1 and minivan C0. So let's say these two cars can be described by the average speed. So basically here we make a simplified assumption. Just say the two car, the feature we want to measure is their average speed. Like if you have a sports car, probably you tend to drive a little bit faster. If you have a minivan, you drive it a little bit slow. So then I do, let's say if I only know the average speed of a particular car they drive, and I don't have the image, I don't know anything, I just see, let's say a point, maybe on your GPS, I able to receive your GPS, I can calculate how I know how fast is that car. Then based on that observation, I want to infer, is this a sports car or minivan? So I hope that problem looks okay to you. Yeah. So now what you can do is what? You just try to assume there's two Gaussian distribution. Let's say if this distribution capture the sports car, then this distribution capture the minivan. So if we are able to estimate these two distribution, then any future observation, it's like on the GPS point, I see a point is moving, then I try to calculate its average speed, then I just plug in and see which distribution is more likely to come from. It's almost like the E step when we are trying to do this GMM, right? So and now we can even see more links to Gaussian mixture, because we define our naive Bayes model according to the following properties, following probabilities or distributions. First is a PC0, PC1. This is called prior probability of class 0 and class 1. We have this term for our Gaussian mixture model, right? Because remember, we are using the pi 1, pi 2 to define this, right? We are assuming that is, although there we are call it a weight or something, but that is essentially the probability of a particular class appeared, right? So here is the same thing, is a prior probability, because, for example, if the sports car is so rare in a region, and this region majority of cars is minivan, then of course that will affect your decision, right? Because even you see now you see a car run at a higher speed, because 90% of the car you have seen in this region, they're all minivan. So that will reduce a little bit of your confidence to say this is a sports car. So that is the reason why the prior probability also matters. But a lot of times the prior probability, you can either calculate from your labels you collected. You collect some data and you see how frequent a different class appeared, or you can put a belief. Let's say you believe for the gender there's a half. That is also your prior. Or sometimes you have no idea. You can put 0.5, 0.5 to each. You just assume basically you do not use any prior. So that is we will talk about more details about this. And let me just finish this sentence, then we will dismiss. And then we have another one is the actual distribution for class C0. So that means if this is a class C0, class C0, how likely to observe a particular point? This is actually, we also see that we are plugging into a Gaussian to compute about this. Right? So let's stop here, and I will see you on Monday.